Okay, question 2M1 from second edition of Statistical Rethinking. So here's the question right here. I'll read it out loud. Recall the globe tossing model from the chapter. So again, the globe tossing example is you're in a group of people and you have a globe representing the Earth and you're tossing it around. And every time somebody catches it, their index finger lands on the globe on either water or land. And so as we toss the globe around, we're trying to tally up how many times somebody's index finger lands on water versus land. And then we're going to use that to try to guess how much of the globe is covered in water versus land. Okay, so recall from the chapter, the globe tossing model. Compute and plot the grid-approximate posterior distribution for each of the following sets of observations. Now, the grid approximation is one method of finding the posterior distribution that we'll use here, but it's just one of many methods that we'll get to in later chapters. So in each case, assume a uniform prior for P, where P is the proportion of the globe covered in water. And so our three sets of observations are here, okay, where water is represented by W and L is land. Okay, so let's start tackling this. And so the first thing that we'll do is we need to tell the computer all of the possible proportions of water. Okay, and so I'm going to put that into a vector here called W grid. Okay, W for water. And when I run this, you'll see that it's just 101 values that go from 0 all the way to 1, where each value represents a possible proportion of water covering the globe, right? So 0.07 represents the possibility that 7% of the globe is covered in water. And similarly, 56 or 0.56 is the possibility that 56% of the globe is covered in water. Okay, so now as we start to visualize these things, these values, these W grid values, are going to be plotted on the x-axis of these grids. Okay, so this plot is empty right now, but the W grid values are the x-axis. Again, these are representing the possible proportions of water that are covering the globe. So the next thing we'll do is we'll try to create a prior probability distribution. Now again, a prior probability distribution is trying to represent our beliefs prior to seeing the data. And so in this case, I'm going to have a prior probability for every value of W grid. So in other words, I'm going to have a value for 0.49. And that prior value, that prior probability, will say, before I've seen any of the data, I believe it is X% probable that 49% of the globe is covered in water. And similarly for 0.69. My prior probability for 0.69 is my prior belief, before seeing any of the data, that 69% of the globe is covered in water. Okay? So every value in W grid is going to have a prior probability associated with it. Now, in our case, the question asks us to use a uniform distribution, a uniform prior probability distribution. And that means that my prior for every value in W grid is going to be the same. Okay? And so let me run that here. And so again, you'll see 101 values, one corresponding to every value in W grid, of the same value. And why is it the same value? Again, it's because we're considering a uniform prior distribution, which means that we believe that any proportion of water is possibly correct. We think that they're all equally probable. Okay. Now, in all truth, in this instance, because we're using a uniform prior distribution, we don't actually even need to do this step, but we're doing it for thoroughness. And later on in this problem and in other questions, we'll see what happens when we can't assume a prior distribution or don't want to assume a prior distribution. Okay. So let's plot our prior distribution right here. Okay. So again, on the x-axis is our W grid values, the possible proportions of water. And then on the y-axis is the probability, or the probability density, or mass, or depending on how you want to think about it in this particular case, of each of the potential values of W grid. And you'll notice it's just a flat line, meaning every value of W grid we think to be equally likely before seeing any of the data. Okay. So now we're going to create the likelihood, the second part of Bayes' theorem, and we have 3 different observation sets, so we'll create a likelihood for each of these observation sets. Okay. And so likelihood 1 for water, 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 land, so on and so forth. Okay, so we're going to model this with a binomial distribution, and it's a binomial distribution, or we're modeling it as a binomial distribution, because there's only 2 possibilities on the globe. Either my index finger lands on water, or it lands on land. Okay, and so this is the code in R that we use for making binomial distributions, and in this case, I say, okay, I want a binomial distribution that shows 3 cases, 3 instances of water, in this case, out of 3 draws. And I want to know the probability of that happening for every value of W grid up here. Okay? So in other words, I want to know the probability of getting 3 waters and 3 draws if the probability of water, or if 6% of the globe is covered in water. And similarly, I want to know the probability of getting 3 waters and 3 draws if 53% of the globe is covered in water, and so on and so forth. Okay. And then for likelihood 2, very similar. We want 3 waters out of 4 draws for every value in W grid, and then 5 waters and 7 throws of the globe for the third one. Now, one thing to notice here is that the observations are being given to us in a particular sequence, right? Land, water, water, land. But that is not specified in our code. And the reason that we're going to say that that's okay is because we're assuming that every toss is independent. In other words, just because I caught it and I found water, my finger landed on water, that doesn't make you any more or less likely to catch the ball with your index finger on water. Now, that's an assumption that we're making, and maybe it's a good assumption, maybe it's a bad assumption, but that's what we're making here, and that's what allows us to ignore the order of the data in this case. Okay. So here's my likelihoods. I've ran them, and so now let's look at them plotted. Okay. It's a little bit scrunched up here, but we have 3 independent or 3 different likelihoods, 1, 2, and 3. And here's the W grid values, and then here is the likelihood on the y-axis for each of these. Okay, so let's just look at these a little bit. So the black curve represents water, water, water. Okay. Now you'll notice that if I go all the way down to 0, that 0% of the globe is covered in water. There is 0% chance of that being the case. Why? Because I've seen water, so there's no chance that there's no water. However, I have not seen any land, and so that means that there is the possibility that there is no land. In other words, 100% water. And in fact, because our sample in this case saw no land, that is the most likely value according to this sample. Okay. Now, once I go to the likelihood 2, where I have the same data, but then I find a land, I have a land observation. Now, I still, here on the red, there's still no chance that there's no water, but I've seen land. And so there is a chance, or there's also no chance that there's no land. In other words, 100% water is also not feasible. And actually what you get is a peak that's around 3/4, around 75%, which is what we found here. It's not exactly at the hovering over 75% just because of how the binomial distribution works, but roughly. Okay. And then similarly for likelihood 3. All right, so we have our likelihoods and we have our priors, and so the next step is to combine the likelihoods and the priors and run these through Bayes' theorem. So when I have the likelihood and the prior here, okay, the resulting values that I get are not going to be a probability distribution. So let me unpack that a little bit. So a probability distribution, one of the things that it has to have is that the area under a curve, so if this was a probability distribution, the area under the curve would equal 1. meaning 100%. And this makes sense because our posterior probability should be representing the probability of every possibility of whatever we're thinking about. In this case, every possibility of how much of the water is or how much of the globe is covered in water. Okay, and so that we assign every possibility and the probability of every possibility to sum to 100%. But there's no reason for a likelihood and a prior, when you take the product of them, to sum to 100%, okay, or to be 100%. And so in order to make sure that they sum to 100%, we have to normalize them. So you notice that I've called these likelihoods, or the prior times the likelihood, the unnormalized posterior. And so we need to divide by a constant, which is the marginal probability here. And the marginal probability is just simply the sum of every prior times likelihood. So the prior times likelihood for every value in W grid. Okay, and so then that will give us the different posterior distributions, the normalized posterior distributions. Okay, and so I'm gonna run that code here. All right, and here's our posterior distributions. You'll notice that these look very, very similar to the likelihoods up here. Okay, and in fact, the shape of these likelihoods and posteriors are identical, and you see that here. So here's the likelihood 1 and posterior 1, likelihood 2, posterior 2, and you'll notice that the shape is identical. And the reason that they're identical is because, remember, this likelihood, I just multiplied it by the prior. Well, the prior was a flat line, so the prior isn't giving any more or less probability to any particular value of W grid. Okay, so the shapes are exactly the same. Now, the likelihood and the posterior differ in the y-axis values. That's not important here, but you'll notice that the y-axis values are quite a bit different, and this just has to do with the fact that a likelihood is not a valid probability distribution, but the posterior is, right? And that's what we went through when we were normalizing everything. Okay, but the important thing here is that that when we combine a uniform prior with our likelihood, we don't change the shape of the posterior distribution. I wonder if I can just zoom in on one of these here. So let me just take this one. Okay, so here we have the posterior for the second set of observations here. Okay, and so in order to read this, I would say, so let's say I went to 0.2 here, so the possibility that 20% of the globe is covered in water is, and this would be the probability density for it, and you can tell it's not very high. And the most likely value is around 75%. Okay, around 75%. So, and that matches what our data was. Okay, so that's the solution to this problem, or my solution to this problem, but let's just explore a little bit further. So again, we've been looking at this flat, this uniform prior distribution, but that's not a very good assumption, right? We don't think that it's very likely that only 1% of the globe is covered in water, and we know that probably 99% isn't covered in water. It's somewhere in between, okay? And so let's just say, for the sake of argument, that we think that roughly 60% of the globe is covered in water, okay? So I'm going to create a new prior distribution that somehow reflects that. And so I'm going to have a prior probability distribution that I'm going to say is a normal distribution that is centered on 60%. In other words, I most think that 60% of the globe is covered in water, and then I'm going to have a little bit of a standard deviation of 10%, and I'm just going to plot that right here. Right, so this is our new prior distribution. Remember, before it was just a straight line all the way across, but now it's a normal distribution. Okay, centered at 0.6. So now with this with this prior, I'm going to rerun the posteriors. Okay, and so again, here is the prior distribution. It's the same in each case, and here's the likelihoods that we've seen before. These are not changed. But now notice, say in this first column, it's very apparent. But now when I have a non-flat prior and I combine it with my likelihood, I completely change the shape of the posterior distribution. So here's this posterior distribution. You see it goes up and then down, whereas previously with the flat prior, it just went up. It just exactly matched the likelihood. Okay, and similarly for the other two cases, the normal prior is changing the shape of the posterior distributions.